Okay, then let's continue. So the next presentation is on one of the trends that Heinz already mentioned. So we will have Cyril Allenspach from the Zurich University of Applied Science, who works with Professor Franz Baumgartner, an old friend of mine. And he will talk about an efficiency comparison between PV string and decentralized module inverters. Cyril, the floor is yours.
Yes. Thank you very much. And I would like to say good morning, good afternoon, and good evening also to everybody being here today. So I will share my slides. Should work fine, I hope. Yes, as has been said before, I will talk about the research we have with also module level power electronics, especially with the efficiency and performance comparison with PV string inverter systems. And here you already see some power optimizers that we tested. So we focused on power optimizers. We haven't looked at other module level power electronics such as microinverters or AC modules, but our focus is on power optimizers. And now when we are looking at residential and residential PV solutions, plants, the installer is also confronted with very different shading objects for those plants. So on this single family house on the left side, you see there's the chimney and there's the shadow, and this can heavily affect the performance of the plant. So this is one of the key features of those power optimizers to improve a system that is shaded, or also that has different powers of power outputs of the modules. And it is a difficult thing to estimate the performance of these power optimizers with so many different shading objects that exist. But we developed first off a simulation tool where we can really compare the string inverter, like the classical string inverter system, against the power optimizer system, so the DC optimized system, and show how they perform when compared to each other over a yearly simulation. And so why is this an important topic? And 2 weeks ago, I've had the pleasure to be at the Intersolar 2021 in Munich, and I also had a presentation as part of the International Energy Agency. But when I went to the fair, there were different also companies that offer those power optimizers. And now if an installer or somebody who's planning also plants and these products look at these data sheets, or information, those marketing information, they will see something like DC optimized system with 39.9% more yield over the year, or up to 30% more energy, and also this description, which is also really interesting that they provide. But often it's a problem of that there are comparisons which are not helpful for the installer, which is sometimes they compare different roofs, different installed systems, so the shading objects will be different, and also it's not the same system, and therefore we need to have indoor measurements and testing for these systems, so we can really input the same voltage, current characteristics and see how they really perform in these conditions. So first off, I want to go back to the basics. I don't want to get too technical, but to show how this looks like also with the performance of these optimizers, we have, once again, I've shown here the different info of our simulation tool. And the simulation tool, of course, is the performance calculations are based on our lab measurements. So it's not just some estimations. So it's really the behavior of the optimizer system and string inverter system. So how they perform for different voltages, for different powers, so that we can really see the difference. Now, first off, it's kind of building this system with the shading object, with the shading obstacle. And here we see also the shadow that goes on this module over the day. And what is different when we have power optimizers? The power optimizers have the capability to DC optimize. This means at the module level, they can track a different power than a string, like a traditional string inverter based system would track. So if we look at these, this voltage current characteristic, the string inverter based system would probably track this point for this module. But here we see the power of this module, and this would be lower. So with optimizers, it's able to track this point and get this additional energy or this additional power in this instance. Because the string inverter system would need to lower the current for the whole plant if it is in series, like the modules are in series. It would need to lower the current of the whole system, and this would, of course, lead to lower power in the other modules. And now, if we look at the difference of string inverter system and the system which is DC optimized with the power optimizers, this can once again be seen throughout the day. This is a daily simulation that we've did. And we also have those different efficiency values of the optimizers shown here, which change over the day with the voltage and the power that this working points or operating points have at this instance. And here we see at this moment in time, which is shown also here in the simulation, and the focus is now on module 12. We see there is a little shade, and this is shown here. And in this instance, the string inverter system and the module power electronic system would track the same point because there is more power in the module at this operating point than there is at this point. So it will be the same. At a later point in the day, at 11 o'clock, 11:30, this point will change because the shade will affect module 12 even more in this case. So we have now a higher power, like a higher local maximum for this module over here. The string inverter system will not track this point with the higher power, because then the current will be lower for the whole system. So now here the DC optimizers has this additional yield at this instant. Now to the laboratory setup that we have. So we have PV simulators that are able to receive voltage and current characteristics and values as an input, and they will put out these values based on, they build an IV curve of a module, and with the same power, same current voltage, and the output of the electrical output will then go into those tested power optimizers. This can also be seen here. So on the left side, there is the solar array simulator. This will provide the IV curve. Now we have the these DC-DC converters, the power optimizers, and they are connected here with the inverter of the power optimizers. And now the same can be done just with a classical string inverter system without the optimizers. And these are, of course, measured. So we have a measurement device at every optimizers, also at the inverter, to really see the calculate the performance and efficiency over time. So if you look at the efficiency values of these power optimizers, well, they're the biggest player for power optimizers is, of course, SolarEdge. And they show in their data sheets that they have values of a weighted efficiency 89.8 and 99.5 for maximum efficiency. And Tigo Energy, which is also a big player for power optimizers, they didn't choose to show any efficiencies, but they just state that it improves the energy efficiency of these underperforming PV systems. Now, approximately 10 years ago, there was a publication by Roland Bründlinger, which is a colleague, friend of Franz Baumgartner, my supervisor, and he published those efficiency values which were stated back in the time. So there has been some kind of increase of 1% to nowadays. The thing is now that these efficiency values stated in the datasheet, there is no standard, no regulation how to calculate and measure these efficiencies. So this is what we've done to measure the efficiency and the performance. On the left side, there is this big graph with all the measurement points. So these are efficiency values for the power optimizers, kind of every possible operating state there is. And on the other hand, we have the color, which shows the voltage ratio. This is very important because we have these DC-DC converters, and their performance, their efficiency is heavily dependent on the voltage that goes in and out, like this voltage ratio. We can see it pretty good that we have around 1%, this green color, and the green color shows also a lot higher efficiency values than, for example, when we have extreme differences in voltage. So there is more losses for like switching losses, which will happen in this case. Now, to show it more in a way where you can understand what is happening at the efficiency of those power optimizers, we have plotted those operating points here again. So on the y-axis, we have the power of the power optimizers and of the operating point. And now we have the K factor, which is again this voltage ratio. And we see here again colored the efficiency values, and we can see it strongly changes for different operating points. So if something is not this, if we want to have, we would like to have the same voltage in and out, because then we have no or little switching losses, and therefore we can see those high efficiency values. But in the end, it can often happen that most of the year we are in a different operating point where we have those a lot lower values, and this should be tackled. And these are not shown in the data sheet, so there must be a way to show the performance and have a standard to also to compare it to string inverter system. Here again, we have this function of the static losses we would like to offer also as a standard. So it's still in development, but we are Franz Baumgartner is part of the IEC, and he wants to see this as a standard as well. So before it was just a static efficiency. So this means it's just dependent on the operating point, what kind of efficiency we can expect. But on the other hand, we have a system, or often a system, which have different shading objects, and we need to assess how the performance varies throughout the year, and how much performance or how much more yield we can really get with these with the power optimizers. So maybe sometimes it's better to have a standard string inverter system without optimizers, and sometimes it's better to have those power optimizers to have more output, more energy over the year. And what we want to do is we want to define different, or the most common shading objects. We also want the input from industry, because this is very important. We want to know which are the ones which we have most likely on our rooftops, or they have installed. And if we have those objects and those planned setups, we can define the different points or states in the year. We now have different IV curves, and if we sum that up and we weight it, we will receive as a sum the output performance of the optimizer system over the year. And this will be a percentage number against the power or the energy that could be provided by the modules themselves. So before they have losses, or before they have losses over DC-AC conversion, so before the inverters or before the DC optimizers. So we can track the same points also with the string inverter system, or input them and test them. So we will definitely see the difference of both these systems. So this is the goal in the end. So in the end, we can see there are results that we have from our lab measurements. So we often see also 2% less lower values of efficiency than the datasheet maximum efficiency. So we need values which are more realistic and display the performance for operating points that make sense for the plant. And really important is that the input voltage is the same, pretty much the same as the output voltage, or so that it should be implemented also as a system design for installers, that they should look that we are always pretty close to those same voltage states. For a system with the chimney, we had a 1.2% gain in this annual efficiency for the power optimizer system against the string inverter system. But this of course can also vary with different inverters that we test, or different power optimizers we can test, but these are just the first performances we see. And these numbers here are now the weighted efficiency over the year that I've just showed the page before, the slide before. And the simulation tool is a good thing, but it's not the right choice for installers, because it's time consuming to set up a system for for every new plant you face as an installer. So there needs to be a standard of kind of just defining the values in the data sheet to which operating points should be tested. And of course, we have we are part of this International Energy Agency, and we are in discussion also with the IEC Task 82. So we will try to get also informations from inverter companies, from power optimizer, DC optimized companies, installers, research that they can also test these systems, have their own testing to really get a good result and a solution for the data sheets that will hopefully provide a good measure to the performance and efficiency of the power optimizers. So just as background, these are kind of the sources and the information or the background of these pages that you've seen of the presentation. And here is also the presentation I held at the Intersolar 2 weeks ago. And also I want to thank really much the International Energy Agency, PVPS, Task 13, Subtask 1.3, and we are also funded by the Swiss Federal Office of Energy for our research. So I thank you very much for your attention. I'm finished with my presentation and I'm open for questions from your side. Thank you.
Okay, Cyril, thanks a lot. I think the topic is a very hot one. So Franz Baumgartner basically has a YouTube video. It's in German language and it has really over 15,000 views, which is quite a bit for such a technical topic. But apparently there is an interest in the community about this topic. So have you also looked a little bit at potential, because you looked also into economics and you simply said that with 1% actually it can be the price can be 10% higher. So how is pricing at the moment, and how do you see the market potential for optimizers these days? Because at the moment it's not so many companies offering it, right?
Yes, I mean, there is just those few big players and new companies coming up. So it is hard to also get entry into the market, but the potential is huge. So I think there in the residential PV inverter market share of the US, Solar Edge has 60% of the market share or even more. So in the US, it's most systems are in the residential sector are DC optimized, use those power optimizers. And in Germany, it's also increasing. Yeah.
But is it a question also of system price? In the US, systems are obviously much more expensive than in Europe, and that's why you can sort of hide higher costs. Right.
I think it's maybe, but also I think it's due to also the safety capabilities. I mean, it's not the only selling point of power optimizers that they perform better or they have higher energy output, but they have different features, rapid shutdown capabilities, which were also mentioned before. And these things are important in the US already and become increasingly important in Europe, also Asia. So I think this is important, but also it's a nice feature to see the performance or power of every module of your plant. So there are also those photovoltaic fanatics, so to say, the customers who want to see their module and in real time the performance, and this can be provided by the power optimizer. So maybe this also plays a role.
So I think there are a couple of questions also on the chat. So I think one point is obviously also O&M. You have much more electronic parts in your system with all these MPP trackers. And so, have you looked into actually also O&M and mismatch, future-proofing, such questions?
Yeah, well, we are mostly looking at the performance because it's a huge topic. But of course, we have more parts, which and also it's sometimes difficult for the installer to change the optimizers. I think Solar Edge offers that if they have a long I think 30 years warranty on their optimizers, or maybe even 35. So they will pay for the optimizer if it fails. But in Switzerland, for example, we have high labor costs for these installations. So this part won't be covered. So it can be also very interesting to look at these topics. Yes.
Okay. Have you also looked into microinverters? Because in that study it wasn't covered, which is also interesting. I think Enphase has also quite a market share in the US. They're trying to get into Europe, but in the US they are very strong.
Yeah, we will look at it slightly, but we will focus on the power optimizers, because in the end it's a different component. It's again kind of just a smaller string inverter, so they say, at each module. So it's technically different than what we look at, but I can recommend the studies or research of Dan Riley from Sandia in the US. He looked at the performance of AC modules, like fully integrated microinverters in the modules. And I think they also looked at microinverters. So they have those parts it's quite interesting what they had on research there.
Okay, cool, thanks. I think there are still a couple of questions, because obviously the topic is a big one, simply because Solar Edge, although they were pretty lowly in that field, gained quite some market share. So there were a lot of arguments and pros and cons against optimizers. It would be great if you could address some of the questions also in the chat, Cyril, and then we continue there.
Okay, that's good. Yes, I will do so. Okay.
Yeah, okay,
thank you very much.
Thanks a lot for this great insights into
Thank you too.
optimizers versus string inverters.